applications. I mean, the new knowledge of the law, it has a lot of applications. It keeps people in their seats and so on. But it has the knowledge of the law has few practical applications, relatively speaking, compared to the other laws. This is one case in which I picked an atypical example. It is impossible, by the way, by picking one example of anything, to avoid picking one which is atypical in some sense. That's the wonder of the world. The only applications I could think of were first in some geophysical prospecting, in predicting the tides, nowadays more modernly in working out the motions of the satellites and planet probes and so on that we send up, and also modernly to calculate the predictions of the planet's position, which have great utility for astrologers to publish their predictions and horoscopes in the magazines. That's the strange world we live in, that all the advances in understanding are used only to continue the nonsense which has existed for 2,000 years. Now, that shows that gravitation extends to the great distances, but Newton said that everything attracted everything else. Do I attract you? Excuse me, do I attract you? I was going to say, excuse me, do I attract you physically? I didn't mean What I mean is, is it really true that two things attract each other? Can we make a direct test and not just wait for the planets and look at the planets to see if they attract each other? And this experiment, the direct test, was made by Cavendish on equipment which you see indicated on the next slide. If I got my slides right. Well, I made a mistake. I was talking about the importance of the gravitation. I was overwhelmed by my clever remark about astrologers and forgot to mention the important places where gravitation does have some real effect in the behavior of the universe. And one of the interesting ones is the formation of new stars. In this picture, which is a gaseous nebula inside our own galaxy, and there's not a lot of stars, but it's gas, there are places where the gas has been compressed or attracted to itself here. It starts perhaps by some kind of shock waves to get collected, but the remainder of the phenomenon is that gravitation pulls the cloud of gas closer and closer together. So big mobs of gas and dust collect and form balls, which as they fall still further, the heat generated by the falling lights them up and they become stars. And we have in the next slide some evidence of the creation of new stars. It is unfortunately harder to see than I thought it was when I looked at it before. But this is not exactly the same as this. This bump here is further out than here, and that this also has a new dot here. I have found better examples, but we're unable to produce a slide. There is one example of a star patch, a light that grew in a place within 200 days. So that when it was in the same kind of a condition of a gas cloud, when the gas collects too much together by gravitation, stars are born. And this is the beginning of new stars. So the stars belch out dirt and gases when they explode sometimes, and the dirt and gases then collect back again and make new stars. Sounds like perpetual motion. I now turn to the subject I meant to introduce, which was the experiments on the small scale to see whether things really attract each other. And I hope now that the next slide does indicate, this is the second try, Cavendish's experiment. The idea was to hang by a very, very fine quartz fiber a rod with two balls, and then put two large lead balls in the positions indicated here next to it on the side. Then, because of the attraction of the balls, there would be a slight twist of the fiber. It had to be done so delicately because the gravitational force between ordinary things is very, very tiny indeed. And there it was. And it was possible then to measure the force between these two balls. Cavendish called his experiment weighing the Earth. We're pedantic and careful today. We wouldn't let our students say that. We would have to say they're measuring the mass of the Earth. But the reason he said that is the following. By a direct experiment, he was able to measure the force and the two masses and the distance, and thus determine the gravitational constant. You say, yes, but we have the same situation on the Earth. We know what the pull is, and we know what the mass of the object pulled is, and we know how far away we are, but we don't know either the mass of the Earth or the constant, but only the combination. So by measuring the constant and knowing the facts about the pull of the Earth, the mass of the Earth could be determined. So indirectly, this experiment was the first determination of how heavy or how massive is the ball on which we stand. It's a kind of an amazing achievement to find that out, and I think that's why Cavendish named his experiment that way instead of determining the constant in the gravitational equation. Weighing the Earth. Oh. He incidentally was weighing the sun and everything else at the same time, because the pull of the sun is known in the same manner. Now, one other test of the law of gravitation is very interesting, and that is the question as to whether the pull is exactly proportional to the mass. If the pull is exactly proportional to the mass and the reaction to forces, the motions induced by forces, the changes in velocity, are inversely proportional to the mass, that means that two objects of different mass will change their velocity in the same manner in a gravitational field. Or two different things, no matter what their mass, in a vacuum will fall the same way toward the Earth. That's Galileo's old experiment from the Leaning Tower. I took my young son of 2.5 to the Leaning Tower of Pisa, and now every time a guest comes, he says, Leaning Tower. So, anyhow, it means, for example, that in a satellite, a man-made satellite, an object inside will go around the Earth in the same kind of an orbit as the satellite on the outside, and thus float in the middle, apparently. So that this fact that the force is exactly proportional to the mass and that the reactions are inversely proportional to the mass has this very interesting consequence. The question is, how accurate is it? And it has been measured by an experiment by a man named Voss in 1909, and very much more recently and more accurately by Dickey, and it is known that 1 part in 10,000 million, the mass is exactly proportional. The forces are exactly proportional to the mass. How it's possible to measure with that accuracy, I wish I had the time to explain, but I'm afraid I cannot. It's a remarkably clever. I'll give a hint, Howard. I'll give one hint there. Suppose that you wanted to measure whether it's true for the pull of the sun. You know the sun is pulling us all. It pulls the Earth too. But suppose you wanted to know whether you had a piece of lead here and a piece of copper here, or polyethylene and lead. It was first done with sandalwood. Now it's done with polyethylene. Whether the pull is exactly proportional to the inertia. The Earth is going around the sun, so these things are thrown out by inertia, and they're thrown out to the extent that these two objects have inertia. But they're attracted to the sun to the extent that they have mass in the attraction law. So if they're attracted to the sun in a different proportion than they're thrown out by inertia, one will be pulled toward the sun and the other away. And so hanging on another one of those Cavendish quartz fibers, the thing will twist toward the sun. It doesn't twist to this accuracy, so we know that the sun's attraction for these two objects is exactly proportional to their centrifugal effect, which is inertia. So the force of attraction on an object is exactly proportional to its coefficient of inertia. In other words, its mass. I should say something about the relation of gravitation to other forces, to other parts of nature, other phenomena in nature, and I'll have more to say of a general quality later. But there is one thing that's particularly interesting, and that is that the inverse square law appears again. It appears in the electrical laws, for instance, that electricity also exerts forces inversely as the square of the distance, this time between charges. And one thinks perhaps inverse square of the distance has some deep significance.